Okay, so in this lecture, I'm going to talk about isotopes, and then we'll talk about how isotopes can be used medically. You'll remember from our discussion of atoms that the nucleus contains the protons and the neutrons. And so, for example, when we look at carbon, remember we had the carbon symbol in 6 and 12. So this means that there is actually 6 protons, and if you add 6 plus 6, then the atomic weight or the atomic mass would be 12. So this is the number of protons. That is the atomic number. This is the atomic weight or the atomic mass. So because 6 plus 6 equals 12, I know that this is a relatively stable form of carbon. So this is a very common form of carbon. So we can also look at carbon that is C6 and C14. So in this particular instance, in order to account for the extra mass here, we know that there has to be extra neutrons. And that is fundamentally the definition of an isotope. It is an atom that has a different number of neutrons. So this is carbon 14. And this is an atom with a different number of neutrons. Notice that they still have the same number of protons. So there's still 6, but in this particular instance, there would be 8 neutrons. So the way that this works is that this carbon-14 is less stable, and so it is going to start to decompose. And so it is an isotope that's going to start to break down. And so it's going to release some energy, and this is actually the element that they look at when they're trying to date, when they're trying to carbon date things. So there's actually some carbon-14 in our atmosphere all the time, and we incorporate it into our bodies, but once we die, we stop incorporating it into our bodies. And so over time, the amount of carbon-14 actually decreases because carbon-14 will begin to decay. So that's what an isotope is, and there are many elements that do have isotopes, not all of them. But one example that is interesting is the isotopes of hydrogen. So this is hydrogen right here. So we would draw this. This would be my elemental symbol, and I would say 1 and 1. So notice that there are no neutrons there, but there is 1 electron. So this would be positive and this would be negative. And so that is what we call a hydrogen atom. That is a very stable atom. Sometimes it loses its electron and it becomes a proton. And we'll talk about that in terms of water and chemical reactions. So this would be the stable one. You'll notice here that this one is going to be deuterium. So that means that it is going to have an extra element in the nucleus. So this is the negatively charged electron, this is the proton, and the neutron is 0. So if you add these two up, that gives you a unit mass of 2. Deuterium is sometimes used to create what is called heavy water. And you can actually track that water through chemical reactions and even in the body through chemical reactions. Another example is this one. And so all of these would be isotopes because they have different of hydrogen because they have different numbers of neutrons. And so in this particular example, there is 2 neutrons and 1 proton and 1 electron. I know that there can only be 1 proton because there is no positive charge, and because the atomic number is 1, I know that is the same. So the atomic number is the same for all of those, so they are the same element. So tritium is actually sometimes used to cause things to fluoresce. And so here's an example of a tritium illuminated watch. And this is not particularly dangerous. I mean, they recommend that if you have one of these, you don't sleep with it under your pillow. But it's not particularly dangerous. It is releasing energy, and it is causing light. So it's releasing light energy. So remember, sometimes isotopes are not stable. And over time, this has a lifespan of like 12 years or something like that. And so over time, the watch will lose its ability to glow. So there is a famous historical use of a radioactive ion for the exact same purpose. And this is radium. So this is not necessarily an isotope, but radium itself is radioactive. And it has a atomic number of 88. And so remember, the first shell has 2, and then each subsequent shell has 8. And so this has 2 electrons in its outer orbit. So 2 electrons in outer orbit. And you'll remember that atoms are happiest when they have 8 electrons in their outer orbits, besides that first orbit. And so this is not particularly stable. And so you can actually find this in a form where it has interacted and sharing or exchanged electrons with nitrogen. It's rare on the planet, and it generally you don't find it in this form that is radioactive. So we have historical precedents for using radium, and we have what are referred to as the radium girls, which were actually women. But in the World War II, there was a desire to have clocks and watches that glowed in the dark. And so they were encouraged to paint using this radioactive, or they were hired to paint using this radioactive paint. And they were encouraged to actually lick their paintbrushes periodically in order to get a more fine, precise line of paint. And so what this led to, because this is a radioactive material, this led to cancerous growth, specifically like in the jaw and the mouth region, the face region. And so this is interesting example of a radioactive substance that was once used and is no longer used in that way, obviously. Okay, so if we look at how isotopes are used medically, isotopes generally are unstable and they emit energy. So they can be unstable and they emit energy. So what you could do is you could label molecules with a radioactive isotope, and sometimes this is what is referred to as nuclear medicine because it has to do with the nucleus of these atoms. So for example, you could label a protein with radioactive sulfur. And that protein, you could put it in the body, and then you could find where that radioactive activity went, and you would be able to trace that molecule in the body. So radioactive sulfur, this is an example, can be used to trace the movement of a protein through the body. So you would create the protein outside of the body, and then you would insert it inside the body, and then you would image the person, and you would look for where they lit up, because that's where the radioactivity was or is. So if we look at some examples of other isotopes, these isotopes are not just used to track the movement, but they can also be used to treat, for example, cancer. Chromium is used to label red blood cells. This iodine is used to diagnostically to look at how fast the kidneys are able to filter the blood. Iodine is used to treat thyroid cancer. So the thyroid is an endocrine gland that uses iodine. So if you have radioactive iodine in the body, it gets stored in the thyroid, and that radioactivity can actually destroy the thyroid. So rather than surgically removing the thyroid, you could use a radioactive iodine in order to treat it. And so these are just some examples of the ways that these examples of isotopes and the ways that they are used. Here's some more studies of electrolytes. If we look at sodium, xenon, pulmonary ventilation, phosphorus, treatment of polycythemia, which means that they have too many red blood cells. So that phosphorus would help to destroy those red blood cells. So here's a diagram or an image that actually shows radioactivity in the body so that you can trace where things go, where substances end up by using isotopes. And so again, this is what is referred to as nuclear medicine.